well, today I'm going to go through 12a, which is the inverse matrix. Today what you want to be able to do is to understand the properties of the identity matrix, know how to find the determinant of a matrix, use the determinant to find the inverse, and then also be able to find the inverse of a matrix by hand and by calculator. So the identity matrix is a square matrix such that A times I is equal to I times A, which is equal to A. So pretty much what you can think of the identity matrix is like the number 1. So anything multiplied by the identity matrix is itself, just in the same way that if I were to multiply any number by 1, it's just itself. So the identity matrix is a square matrix, and it's got zeros everywhere except on the leading diagonals. So a 2 by 2 identity looks like this, 3 by 3. It looks the exact same, but it's got 3 rows, 3 columns, and 1's down the leading diagonal. So the main property of it is it doesn't matter if you multiply it before or after, no matter what you multiply it with, it will always equal to A. So example 27, so if A is equal to this matrix, show that A times I is the same as I times A, which is the same as A. So pretty much I have to do all of these calculations and prove that it's the exact same. So first of all, I'm going to do A times I. So this is my matrix here, and the identity, which is a 2 by 2, that's the one that I'd be using, would be a 1, 1, 0, 0. Remember, when we multiply by hand, what you need to do is that it's row by column, like that. So what we would have is 2 times 1 plus 3 times 0. So I'm not going to write that down. And then we'll have row by column again, 2 times 0. So we're going to do this one here. 2 times 0 is just 0. 3 times 1 is 3. And then we'll have row by column. 1 times 1 is 1. 4 times 0 is 0. And then finally, row by column, once again, we'll have 1 times 0, which is just 0, and 4 times 1 is 4. So as you can see, we're back to matrix A over here. Same thing if I were to do I times A, so set that up 1, 0, 0, 1, and then 2, 3, 1, 4. We'll end up with the exact same. So I'm just going to kind of talk through it because I hope that you know how to multiply matrices by now. So we've got 1 times 2, which is 2, 0 times 1 is 0. 1 times 3 is 3, 0 times 4 is 0, 0 times 2 is 0, 1 times 1 is 1, 0 times 3 is 0, 1 times 4 is 4. So once again, I've got matrix A. And so by showing this calculation, what I can show is that anything times the identity matrix is just going to be itself. The reason that this property is important is because that's how we get around the inverse matrix. So the inverse matrix. Now, just for a moment, remember how we talked about the identity matrix is like the number 1. So anything times the number 1, so say 6 times 1 is going to be equal to 6. So how do I get this number 1? Well, the way that I can get 1 out of that is if I divide the number by itself. 6 divided by 6 is going to be equal to 1. In the exact same way we can multiply this to matrices. Now we know that any matrix times the identity is simply going to be itself. Now if I wanted to get this identity by itself, what I would usually do is divide. However, there is no division in matrices. We do not use division. Instead, what we use is the inverse matrix. So the inverse, the way I take A over to the other side, instead of dividing is I take the inverse of it. So I will equal A inverse of A. And so the identity is simply, and a matrix multiplied by its inverse will always give the identity, whether if it's pre-multiplying or post-multiplying as well by the inverse, they will always give the identity. And that is the basic property of the inverse. So it's like the division of matrices. Any 3 by 3 or larger square matrix can be used using the calculator. What we'll be doing is we'll be doing it by hand for 2 by 2s, and then otherwise you'll just go straight to your calculator. So there are 2 steps to find the inverse. The first step is to find the determinant of the matrix, and then the second step is to rearrange your numbers in that it'll become the inverse. So the quantity AD minus BC is called the determinant of this. Okay, so as you can see, that's ABCD. So if I just multiply these two with each other and subtract BC from it, we will get the determinant. So we denote the determinant as usually by det A, this one over here. But as you can see, there's also the absolute of A or delta A. But the one that's most commonly used is det A. If a 2 by 2 matrix has a determinant equal to 0, what we would say is that it does not exist. So the inverse is undefined. Okay, so you cannot find the inverse of a matrix if its determinant is 0. So that means that a 2 by 2 matrix only has an inverse if the determinant is not equal to 0. So once we've found the determinant, all we need to do is we need to switch our letters around. So A and D switch around physically, so D becomes where A is and A becomes where D is, and then we just simply put a negative in front of B and C, as you can see in this diagram over here. Alright, let's try an example for this one. So for the matrix 5, 2, 3, 1, find the determinant of A. Okay, so the first thing we want to do is label our letters. Here's A, B, C, and D. So that is going to be 5 times 1 minus 3 times 2. So that'll be 5 minus 6, which is equal to negative 1. That's my determinant. And then to find the inverse, what we want to do is exactly in this formula how we have the 1 on the determinant of A, so that'll be 1 divided by negative 1. And then we switch A and D, so we'll have 1 and 5, and then we put a negative in front of B and C. And so we'll have negative 2 and negative 3. And then what we can do is simplify it as well. So 1 divided by negative 1 is just going to be a negative. And then what we can do is take that negative on the inside. So I'll do it first on the outside. So that's 1, negative 2, negative 3, and 5. And then we can multiply that negative to the inside. So that'll be negative 1. Negative 1 times negative 2 is positive 2. Negative 1, so remember that that's a 1 there. So negative 1 times negative 3 is a 3. And negative 1 times 5 is negative 5. And that is what we would say our inverse is. Now part C says show that the A inverse times A is equal to the identity. So this is just a way to be able to check that you really have found the inverse. Let's give that a shot. So here's the inverse over here. Here's A. Remembering our row by column. So once again, I'm going to go through this kind of quickly because hopefully you've got in your head around multiplying matrices. Negative 1 times 5, which is negative 5, and then 2 times 3 is 6, so plus 6. And then negative 1, now we're going to do this one here, negative 1 times 2 is negative 2, and 2 times 1 is positive 2. Then we'll have this row by the first column, 3 times 5 is 15, minus 5 times 3 is 15, and then second row, second column, 3 times 2 is 6, and then minus 5. And so negative 5 plus 6 is 1, negative 2 plus 2 is 0, 15 minus 15 is 0, and 6 minus 5 is 1. And as you can see, we've just proven that this matrix A times the inverse is equal to the identity. You can also do this through the calculator. So let me just pull that up. So we can go menu, add calculator, set up our matrix. So that can be our matrix there. The matrix we used was 5, 3, 2, 1. And what we can do is store this one as matrix A. So that's our matrix there. Now if I want to find the inverse, I can go A to the power of negative 1, and that will give me my inverse. And as you can see, that's exactly the answer that we got before. And also what we can then do to prove that that actually is the inverse is multiply A by the inverse matrix. So A times A to the power of negative 1 will give us our identity. And that's it. That's exercise 12A. So hopefully that's pretty straightforward. Visiting the learning intentions once again, we now understand the properties of an identity matrix. We know how to find the determinant. We know how to use the determinant to find the inverse and how to find it by hand and by calculator. Hopefully it's all pretty easy.